What specific challenges associated with computational overhead in test-time compute methods does the xLSTM-7B architecture aim to address?
The xLSTM-7B architecture specifically addresses the challenges of computational overhead in test-time compute methods by optimizing for both inference efficiency and training stability. It achieves this by employing a linear recurrent neural network design that allows for constant memory usage during inference, enabling faster response times and the ability to run on edge devices. The architecture incorporates improvements such as operating the MLSTM cell in a lower dimensional space and introducing position-wise feedforward MLP layers, which enhance computational efficiency. Additionally, the xLSTM-7B architecture mitigates high-gradient norm spikes and variance through techniques like soft capping for input and forget gates, ensuring stable training at large scales. Overall, these optimizations allow the xLSTM-7B to maintain high throughput and low memory footprint during inference, effectively addressing the increased computational demands of test-time compute methods.
Can you explain how the xLSTM-7B architecture works? Please illustrate its main components and the flow of information step by step, particularly focusing on the MLSTM cell and its operation during both training and inference.
The xLSTM-7B architecture is built around the MLSTM cell, which operates in both recurrent and parallel modes to enhance efficiency during training and inference. During training, the MLSTM cell processes a full sequence of input vectors in parallel, computing hidden states for all time steps simultaneously, which allows for efficient training kernels. In contrast, during inference, the MLSTM cell generates tokens in a recurrent manner, updating its hidden and cell states based on the input at each time step, while maintaining constant memory usage. The architecture incorporates several optimizations to improve performance and stability. For instance, it employs soft capping for the input and forget gates to mitigate gradient spikes, and uses RMS norm instead of layer norm for better training stability. Additionally, the MLSTM operates in the model's embedding dimension rather than a higher dimensional space, which reduces computational costs and enhances GPU utilization. The overall flow of information involves the MLSTM cell receiving input vectors, processing them through its gating mechanisms, and updating its states accordingly, ensuring efficient handling of long contexts and high throughput during both training and inference.
Provide a simplified example that shows how the xLSTM-7B processes input data through its architecture. Walk through the steps from input to output with a focus on the gating mechanisms and state updates.
The xLSTM-7B processes input data through a series of steps involving its MLSTM cell, which operates in both training and generation modes. Initially, the model receives a sequence of input vectors, which are processed in a recurrent manner during inference. The gating mechanisms play a crucial role here. The input and forget gates are computed from pre-activations, controlling the flow of information into the cell state and determining what information to retain or discard. The hidden state is updated based on the current input and the previous hidden state, with the cell state responsible for long-term memory being updated accordingly. This process allows the xLSTM-7B to generate output tokens efficiently, leveraging its optimized architecture for high throughput and stability, particularly through techniques like soft capping of gate values and the use of RMS norm for improved training stability.
What comparative advantages does the xLSTM-7B offer over transformer-based architectures, particularly in the context of efficiency and inference speed?
The xLSTM-7B offers significant advantages over transformer-based architectures in terms of efficiency and inference speed due to its optimized block design and linear scaling properties. Unlike transformers, which experience quadratic scaling in compute and memory usage with increasing context lengths, xLSTM-7B maintains a constant cost per generated token, resulting in faster text generation regardless of input size. Additionally, the xLSTM-7B architecture operates in a lower dimensional space, which reduces GPU memory footprint and enhances throughput, achieving about 50% faster generation than Mamba models and outperforming Llama-based transformers at prefill length 0. The model's design allows for efficient local inference on edge devices, providing rapid response times, which is crucial for user-facing applications. Overall, these optimizations enable xLSTM-7B to achieve the highest prefill and generation throughput with the lowest GPU memory usage among its peers.
Describe the experimental setup used to validate the performance of the xLSTM-7B. What benchmarks or metrics were employed, and what datasets were utilized in the evaluation process?
The experimental setup for validating the performance of the xLSTM-7B involved benchmarking against state-of-the-art transformer and recurrent LLMs on the 7B parameter scale using the Open LLM Leaderboard v2 and the LM evaluation harness. The xLSTM-7B was evaluated on a dataset comprising 3 trillion tokens from the DCLM dataset with a context length of 8,192. For long context capabilities, the ruler benchmark was employed, which includes synthetic tasks with varying context lengths from 4K to 131K tokens. The performance metrics included validation perplexity, accuracy on downstream tasks, and generation throughput, with comparisons made against models like Llama 2, Llama 3, Mamba, and Falcon Mamba. The results indicated that xLSTM-7B ranked mid-range among 7B scale models, suggesting potential for improved performance with larger and better curated training datasets.
What were the notable results achieved by the xLSTM-7B in your experiments, and how did these results illustrate its effectiveness compared to existing models?
The xLSTM-7B demonstrated notable results in various experiments, particularly in terms of inference speed and efficiency. It achieved the highest prefill and generation throughput with a significantly lower GPU memory footprint, compared to both transformer models like Llama 2 and Llama 3, and Mamba models such as Falcon Mamba and Mamba. Specifically, xLSTM-7B was about 50% faster in text generation than Mamba, attributed to its optimized block design, and maintained constant generation speed regardless of input context length, unlike transformers which experienced a drop in speed. Additionally, in long context evaluations, xLSTM-7B outperformed RWKV models and achieved 20% average accuracy at a context length of 131K tokens, despite being trained only up to 32K tokens. These results illustrate xLSTM-7B's effectiveness in handling long contexts and its superior efficiency in both training and inference compared to existing models.